Uh, Now let's look at some vector norms, which can in fact act as matrix norms when applied to Rn cross n. While there are some which are matrix norms and some which does not form a matrix norm. Okay, uh, so there are some vector norms which are valid matrix norms when applied in cross n. So I've already told that we can actually formulate them as an n square cross one vector and apply these vector norms, matrix norms. But we only know that they satisfy all the properties till the triangle inequality. But submultiplicative is a property which you have to prove to show that it's a valid matrix norm. The first one to look at is the L1 norm. Right? We have A, which is Rn cross n. Then the L1 norm of A is given by sigma I comma j is equal to 1 to n modulus of AIJ. So we are basically taking modulus of all the elements of the matrix and adding them together. This is the so is it a valid matrix norm? Let's see. Properties 1 to 3 holds because it's the vector norm since this is a vector norm. We don't have to prove it. Let's look at submultiplicativity. L1 norm of AB is actually sigma I comma j equal to 1 to n modulus of ABIJ, right? How do you write ABIJ? Matrix multiplication is written in terms of a new index k. This is how we write matrix multiplication. AIK, we need a sigma. Sigma over all k is equal to 1 to n AIK into BKJ. This is how we write matrix multiplication. The ijth element of matrix multiplication, right? It's the dot product between the inth column and the ikth column and kjth row. This is how we write it. And so this is less than or equal to. So we can actually, we have to take this summation inside. I comma j comma k. For convenience, here we can actually take another variable as well because it's a dummy variable. To n, a of il, p of kj. This is valid because modulus of the sum is always less than or equal to sum of the moduluses. So this is again less than or equal to, we can actually split them I comma L together and sigma j comma k is equal to 1 to n a of kj. Kj or even if we take the transpose of it, which is jk, it doesn't matter, right? Or you're just taking modulus and adding them together. So why is this so? We're taking the sum of products, but instead, if you take the modulus rather than taking the product and adding them together, if we take their sums and okay, I think we've already seen this this kind of a decomposition, how it both of them are positive. So this is like a product of two numbers. We're taking product of two numbers and adding them. And individually adding all of them. No, this is not less than or equal to, this is just equal to. Yeah, that was one thing I was thinking. Both are essentially the same, right? They're not equal. This is true. This is true. So this is actually the definition for the L1 norm of matrix A, and this is L2 norm of matrix B. These are both equal. Yes. So we can prove that norm of L1 norm of AB is less than or equal to L1 norm of A is L1 norm of B. So submultiplicative holds, hence proved. This is a valid matrix norm. Now let's look at L2 norm. L2 norm of a matrix is defined as similar to what we have for matrices. Sigma ij from 1 to n. We take the modulus for every term, square it, add it all together, and finally we take the square root of it. Is it a valid matrix norm? Again, we have to prove submultiplicativity. Let's look at this. Squared is I is equal to ij is equal to 1 to n. And how do we write the product? Sigma k is equal to 1 to n. Aik bkj. The dot product between these two terms squared. Okay. This is sum of moduluses. I mean modulus of sum. So we can, this is always less than or equal to sum of the moduluses. So this is less than or equal to sigma I comma j equal to 1 to n sigma aik all squared, where k equal to 1 to n, and we can use some other, let's say L, to not confuse between variables. Yeah. L is equal to 1 to n b lk lj, sorry, lj squared, right? Again, we can take I and k together. A of ik all squared sigma j and L together ajk or a Lj, which in fact is the L2 norm of A squared into L2 norm of B squared. So there are a few more things about L2 norm. First thing is L2 norm of A for a matrix. This norm is also L2 norm of matrix A is also called as the Frobenius norm. Okay. So the Frobenius norm, what we're computing, the standard definition is sigma summate over all I j reading from 1 to n A of ij square and take the root of it. Okay, I mean this is the Frobenius norm squared. Is basically you are taking the squares of every element of the matrix and adding it together. Turns out that this is also equal to trace of A transpose A. You basically take A transpose A and you take the trace of it, trace being the sum of all the diagonal elements, right? You add them all together, all the diagonal elements together. Then that is actually equal to the Frobenius norm. You don't have to basically take the pain of squaring every element and adding it. You can actually find the matrix multiplication A transpose, whichever is less expensive, and add all the diagonal elements of that. Uh, matrix A transpose A together. Okay. So there is one more interesting property for Frobenius norm. If A is equal to A1, A2, etc., AN, what I'm meaning here is that you can express this as columns, right? A is a matrix. We can just look at them as individual columns stacked together. Then norm of A2 squared is actually the sum of all these vectors, column vectors, their individual norms, and just adding them together. It doesn't make any difference, just some arrangement, right? And if U is unitary, you've already seen U of X is same as, the norm of UX is same as norm of X. Already seen this because we have the dot product definition, and from dot product definition, it will be X transpose X, which will be UX whole transpose in the UX, but U transpose U is actually is equal to I. In this property, we'll get this is UX, L2 norm of UX will be same as L2 norm of X. So this is one. For this, it's valid. Hence, so if you have a matrix like this, U into A, right? A is actually stack of all these column vectors. So you can individually split it over all these matrices, all these column vectors. This is UA1 squared plus UA2 squared plus etc. plus UAN squared. All these being L2 norms. But we already know that this is norm of A1 squared plus A2 squared plus norm of AN squared, right? Which is same as norm of A, the matrix A 2 squared. So what does it mean? We can actually extend the idea of unitary matrices to from vectors to matrices as well. If you have any matrix A, and if U is a unitary matrix, the norm of L2 norm of UA is same as L2 norm of A. It doesn't have any change. Similarly, if we have two unitary matrices, U comma V, such that the unitary, so what does that mean? U is equal to U into U transpose is equal to I, and V into V transpose is equal to I. Search matrices, no, it's actually U transpose U and transpose V is equal to I. Does changing it have an impact? I don't think so. In that case, the norm of UAV will be same as norm of L2 norm. L2 norm of is same as L2 norm of A. Both are unitary. Okay. So we've looked at two norms, which are vector norms. And now let's look at infinity norm. L infinity norm. So L infinity norm of A is defined as the max over I less than equal to ij less than equal to n modulus of Aij. This is a matrix norm. In fact, this is not a matrix norm. Why is this not a matrix norm? We can prove this. This is not a matrix norm. Proving not a norm is always easy because you just have to take a counterexample. So you have to cleverly choose a counterexample. Let's have a matrix J, which is 1, 1, 1, 1. And we know J squared is equal to 2, 2, 2, 2, which is actually 2 times J, right? The infinity norm of J is equal to 1, while the infinity norm of J squared is equal to 2. But we know that for submultiplicativity, yeah, the norm of J squared should be always less than or equal to norm of J whole squared. Okay, let's put this way. Squared implies 2 is less than or equal to 1, which is not, is absurd. So it is not a valid matrix norm. But, however, the matrix norm defined by n times A infinity as a matrix norm. How do we prove this? Again, we have to prove submultiplicativity. Infinity is given by n times max, 1 less than or equal to ij less than or equal to n, sigma k is equal to 1 to n, aik, bkj. Again, sum of modulus is less than or equal to modulus of sums. Modulus of sum is always less than or equal to sum of modulus, sorry. This is max less than or equal to ij less than or equal to sum of moduluses bkj, which is in fact less than or equal to n times max t. We are actually taking the modulus dot product between okay, yes. Let's go like this, n times sigma. G. This is okay. This is a max term, right? You This is less than equal to or is it equal to? Not really sure. I can put suppose we choose max of aik. This is actually sum of aik. Then what will happen? This is less than or equal to, right? Which is less than or equal to n times max. N less than or equal to ij less than or equal to max of over 1 less than or equal to k less than or equal to n a of ik. We're just adding it up. So this is a sum. We still have the sum, yes. If I just this is more or less values. If we just choose the max of them and add them together, this is in fact yeah, this is correct. And this is sum L is equal to 1 to n max of 1 less than equal to L less than equal to n modulus of Pij, right? This is less than equal to because we have a vector like this. Let's say a1, a2, etc. an, and we have a max value. Let's say ak is the max value. One, we are taking the modulus and adding them all together. The sum of that would be always less than or equal to just replacing it with all ak's, the max value, and adding them together, right? So this would be what is true. But this is a constant value. Right? Summing them together is basically, so we can view this as this is equal to n times max is equal to less than equal to 1g less than equal to n sigma over k is equal to 1 to n. This is actually the infinity norm. Infinity. That is not the right way to put it. What we can do is, this is the max term, so this will be n times a this how do you write this? This is not a infinity, right? What is infinity norm of a? Just have to take max terms for like case. K vary from 1 to n. Also, you have to sum it from all the way to, you have to take, yeah, the indices we have to move, right? Yeah, correct. This will be something like this. Sigma over all n max of n less than or equal to I less than or equal to n AIK. Well, when I'm looking at it, I have two sums. I'm getting an n cube. I think there's some mistake here that we splitted. Will we do this for the earlier step as well? We split the summation together. Two different components, yes. This is actually a constant term, right? This is independent of nk, and take this is just one term, but you're adding it n times. Anyways, let me complete this one. This is j comma l is equal to 1 less than equal to j comma l less than equal to n. No, we have to anyway add them as well. L is equal to 1 to n. Max of 1 less than equal to l less than equal l comma j less than equal to n bij. We'll get n times why am I getting this and again, I'm not sure. There's an additional n which is some mistake which I have to solve. But this is basically the norm which we have. And yeah, there's some clarity required for this. We'll look into it in detail. Okay, let's conclude this. From this, we can prove that norm of AB infinity, where we've defined it as n times A infinity norm, is a valid norm, which is equal to, sorry, this norm n times is a valid norm. So stop the discussion.